So I'll pick up here on resolution. The target strength is a fish length discriminator, and kind of picking up on the last part of Kevin's presentation and investigations, which were impressive. You didn't give up, and informative, but I may modify a couple of my statements in this one based on what you said there. But so this piece has some aspects. My major professor, John Horn at the University of Washington, this target strength in backscatter was really kind of his focus of study, and did a lot of investigations on relative impacts of biological factors and other factors on target strength. A lot of X-ray work and investigation of fish backscattering structures. This is one of the examples from the lab where they do a lot of time series on fish swim bladders and backscattering volume. But just as the intro, going back in the literature, and again, Ken Foote did a lot of work on fish target strength. Target strength was remains a big deal, just being able to measure it in situ. And really in the 1980s, when they first had the ability to do that, initially with dual beam systems, and then kind of in the 90s with split beam systems, which will do a more accurate job of it. It was fairly huge, particularly in the marine community, because having a true measure of what that contribution of the fish to the acoustic return was they were echo integrating, scaling those numbers out, really improved their accuracy. And of course, as you start to get more information, you often find it's maybe less than perfect, but just looking at water as an acoustic medium, I mean, the reason we use acoustics as an assessment technique, it's a very good medium, a very high efficiency medium for transmission of acoustic energy. And why? It's 800 times more dense than air. Andrew talked earlier in the acoustic theory about absorption and spreading losses there, but again, they're well understood. The water's basically incompressible, or nearly so, and so our speed of sound in water is about 4 to 5 times faster than in air. A little bit of hangover from my professor, I guess, but it's worth really what we're interested in measuring, or setting up our systems to work with, are point source targets, where the fish is an individual scatterer. Most of that scattering is coming from the swim bladder. That can be dependent on the frequency. As you move up in frequency, you'll get more scattering from smaller structures and particles, like the Ditson cameras operate up in the megahertz range, and their overall detection range is limited, but they can start to see scattering from the body, and then the swim bladder might be a lesser contributor. But for the most part, for the frequencies we're using, we want to look at targets and use acoustic sampling frequencies where the length over lambda, meaning the backscattering point, or the length of the fish, I guess we can think of, relative to the frequency, is much greater than 1, and it certainly is at 200 kilohertz. I talked a little bit earlier in the sort of a HTI intro about for zooplankton, there are systems out there that will use multiple frequencies and then try to exploit that resonant scattering, where you get a large amplitude return when the wavelength, the acoustic wavelength, is approximately equal to the length or scattering, backscattering area of the target. And then geometric, or things, that's the type of scattering you'd be getting off the bottom, or a big plate type surface, or something where the scattering surface is the length over lambda is much greater than 1. So I guess just kind of an introduction in the sort of 3 primary types of sound scattering. And this would be an illustration of that zooplankton resonant sort of see this transition where back in 1980 Holiday and Piper did some investigations just on targets, plankters and fish, and across a wide range of frequencies, and you can kind of see on the fish on the upper part of the graph where you do get that resonant spike, and then basically kind of a flatline target strength response as you get into the geometric scattering. So so we can see, there is some difference in target strength with frequency, even in the Rayleigh scattering kind of off to the left. So from a biological standpoint, or I guess behavioral as well, and we know this from what Kevin just said on the behavioral end, is those fish change aspect and orientation that can have a fairly significant effect on the mean target strength of the individual. Feeding again might be an aspect type change. Again, my professor was looking at things more so in marine fishes, but found some differences in mean target strength based on the spawning state of some of the marine species, and I think a lot of that had to do with just fat accumulation in the gonads and eggs and production and so on. Ontogeny again, well actually that's really ontogeny, so it's related to that. And morphology, we'll look a little later, again, as Kevin mentioned, and we'll kind of circle back to Love's here at the end of it, Love 1971. There definitely can be some differences in best fit relationships based on the anatomy of the fish, and really what it's presenting as a scattering surface, which is primarily the swim bladder, and can be affected by swim bladder shape and size, and really what cross section it's presenting to the acoustic energy that we're bouncing off it. We'll just kind of walk through this pretty quick. That's kind of a plankton piece, but again, you can have plankters that can have gas inclusions or without, and certainly with fish as well. You can have Physostomus and Physoclistus fish that can, depending on that and really kind of what their state is for achieving neutral buoyancy, can have some effects as well. And there's been experiments with transducers, and walleye pollock is a huge fishery that is managed primarily with these large-scale acoustic surveys that go on in the Gulf of Alaska every year, run by a National Marine Fisheries Service and so on. But so there's been some investigations on contributions of different parts of the fish, and really mapping that into fine scale. But again, the swim bladder is still the primary contributor, but there is some scattering from other structures. And again, swim bladder shape can vary widely in different species. This one to the right, I think, is from the Sea of Galilee or somewhere in Israel, where it actually has two swim bladders, brook trout. And again, just looking at fish of similar size, just looking at them in an X-ray scan, we can see some variability in the swim bladder form and shape, at least from the size. Seems like most scientific things, you start to look deeper, and you can find all kinds of reasons why things would vary. But overall, from just a straight volume, the swim bladder is only 4 to 5% of the fish volume typically, but it is air filled, and we're looking at that 800-fold difference in density from water, and that's really what we're measuring with the acoustics. And pressure effects have been investigated, and then there is an effect of pressure on measured target strength, that they found could be predicted by Boyle's law up to a certain depth, and in some of these earlier studies that could observe changes in swim bladder size in fairly short periods. And again, the foot experiments that found that the Swimbladder was the primary reflector. Again, just looking at a single species, pollock, a marine species, and could find a lot of variability in Swimbladder shape within a species. And again, most of these early experiments that were at 38, 120 kilohertz, but looking at multiple species and measured target strength and in length fits, and in this data, like in some of the data Kevin showed, they've got fit relationships to them, but we do see a fair bit of variability around them. And this one you've seen earlier, just that aspect. This is a really old photo, but I think they hand drew this. But this was actually at 420 kilohertz, where you'll see what you'll see as you go down lower in frequency, you will see less spiky sort of variability, more of a kind of a hourglass or a smooth shape around that. But you definitely can see differences of 15 to 20 decibels, or even a bit more, from full side aspect to head aspect, and
How big is the fish?
I'm trying to remember on this one. This was Bill Aker, the guy who started Biosonics, when he was doing some sea grant work up in the marine environment, and I can't quite remember. This was an adult salmonid, but I think and basically, and again, these were all controlled experiments before they had split beams, so I think these were fish in monofilament harnesses on rotating structures, and then measuring the voltage return from a single beam transducer, looking at the calibration, setting it up on axis, and then measuring in that way. But this was some of the earlier work, just trying to quantify or get a measure of how much difference in backscatter would be measured from a fish based on varying aspect in the beam. And again, fairly idealized kind of piece, and it's a dead fish, which could have some impact on its Swimbladder volume and so on. Yeah, no, I'll just run through this quick. Some other work that was done, again, in very controlled environments with narrow beam transducers, trying to map where the backscatter, the various contributions, getting some increase from the head, but the bulk was on a yellow perch on this one from the Swimbladder. So just a bit of a history of some of the earlier work, looking at kind of what the efficiency of backscatter was based on density of Swimbladder, change in the speed of sound, which is really what happens when the sound encounters a density gradient. It shifts dramatically, and then you get sound backscattering back to the source. These type of measures were really, again, this is really looking at different frequencies, how that target strength could vary, and we typically will see lower variation in target strength as you move down in acoustic frequency. If you were using a 120 kilohertz system relative to a 200, you'd see some diminish in or reduction in the variance, just because you get less contribution from some of the smaller contributors to the scattering. And so again, a lot of the work that was going on at the Fisheries Acoustics Research Lab, involved really looking at X-raying the fish, looking at structures and backscattering properties, trying to sort of define the Swimbladder, and also the Swimbladder orientation in the body of the fish, relative, and then also looking at how that fish oriented in the water column, because what he was trying to really get out of this was, what is the backscattering cross section for these fish, both in a physically measured way, and then looking at, like that previous slide, what the efficiency of the backscatter was. And certainly you can get swim bladders that aren't dorsally, perfectly maybe dorsally oriented relative to the fish orientation relative to the transducer, which again, if we're looking at empirical fit relationships, as long as that's how the fish tend to orient, I mean, we can still map that back to estimated lengths. But there'd been a lot of work, even removing swim bladders, looking at volumes, trying to calculate in that way. And John was trying to look at it, in the fish. I'm sure you've done this as kind of a surgical exercise, but what we can look at what the backscattering contribution is sort of per cross-sectional area, and then relating that. And again, his kind of end game with a lot of this Pollock work, which was his focus, he was and is still employed both at the university and at NOAA, kind of overseeing a lot of this work, was to really try to refine target strength length estimates for the Pollock, again, to kind of feed into that echo integration scaling to get the most accurate estimates of metric tons for managing the commercial fishery. So similar to the kind of things we do, just on a lot bigger scale, bigger money kind of piece. And again, would look at those over different lengths and growth stages, and just trying to see, was that a proportional backscattering surface increase with length. We'll kind of run through the zooplankton ones, but it is zooplankton. You can certainly use even the 200 kilohertz systems that most of us are typically using for zooplankton assessment. The target strength basically on zooplankton is of course much lower, much less than for fish, and most of the backscattering from plankters, again, they're trying to achieve usually some neutral buoyancy, and they'll typically do it through lipids or that sort of thing. And there's a lot of work for plankton then to really map that back into either numbers or weight. Sort of the equivalent of length for plankton in the acoustic world, they usually will call it equivalent spherical radius, which they'll get some relationship between. And really what that is if you could think of just a air bubble of some size that would return that amount of backscatter, and then they'll try to relate that to either overall animal size, and then use that to apportion out different size groups of zooplankton. But again, like most scientists, then they do research. Well, that can vary over the time of year and and so on. So this work, I think, was to then get an estimate of how much this oil they had in them, what that would mean to their equivalent spherical radius, what that might map back to in using acoustics to come up with a numeric estimate. And certainly investigate things like feeding and what kind of effects that had on swim bladder and so on. And we'll circle back here, and these things do have could potentially have, and they do have been found, they have some impact on the swim bladder shape and cross section. I think we'll see later they're not big drivers, but they're there. Pressure effects, again, a lot of this hinges back on some older work, but could certainly see, this was with an Atlantic herring at 25 meters in the surface, that you get changes in the cross section of the swim bladder. And yeah, fish behavior, again, like sort of Kevin showed. I mean, if you're getting a lot of shoaling and schooling, of course, if they're heavily schooled, we may have issues with trying to just identify them as single echo detections, single targets, boat avoidance or predator avoidance, or caught on a jig. can certainly affect your orientation. We've seen that. So behavior definitely is a factor. And this is another marine piece where they really were, and this really just speaks to not so much the fish, but there's been a lot of work in the marine environment because there's these big, multi-million, if not pushing, billion-dollar fisheries on things like pollock and hake. They've got acoustic vessels. They've actually designed boats, big blue water boats that are low noise boats to minimize that avoidance. This was was a measurement where they were actually measuring frequency and how much noise was really radiated from a vessel and bringing it back to different sources. And so this information was used. The International Council of Exploration for the Seas, which a lot of the marine fisheries acoustics.
Are they the ones doing the research, or are these companies hiring their own people to do this research so they can support their fishing efforts?
Well, no, really, this is totally on the regulatory side, and it's kind of divorced from Icicle and Trident and all or other folks that are actually doing the harvest. They're certainly, well, like anybody, they'd like to catch more of them, but really most of that big marine scale management has gone under National Marine Fisheries Service. And then the folks that are actually the serious marine hydroacousticians, there is an acoustics group within ICES that, sets standards for this is really how you should process the data. These are the terms you should use to refer to. And they actually came up with a standard for vessel noise based on some other work where they had measured some vessel avoidance. They've done things like using even AUVs or other work like you did with, Wyoming, where you're doing parallel boat work or different types of vessels. So they've actually gone out and built a number of these dedicated big acoustics vessels. Now again, whether that's something that would translate into the freshwater environment or not, I'm not sure. You can look at some things like with the split beam data, and once in a while on real shallow fish, I maybe have seen something where you can basically look at the track vectors and are you seeing displacement away from the vessel. But again, we're often just getting these very short snapshots on the fish as we're moving through. But so this one really just shows some of the data that went, the sorts of details that they're worried about in these big scale ones. But again, a 20-30% difference in your estimate could make a very big difference in allowed harvest, and it just scales up because of the sheer scale of the tonnage that they're harvesting out in the Gulf of Alaska and over in the North Sea. And this was just an illustration from an earlier pub. They actually have classifications for different school sizes and splits and different types of behaviors that have been investigated. So, and again, like this one may harken back a little bit to what Kevin saw with some of the fish that you're getting long series on, even at dorsal aspect. They're measuring some measurable differences in fish target strength at tail beat cycle. Again, this is echo to echo target strength. And one of the take homes, we always try to get our best estimate of mean target strength because it will vary echo to echo from some different attributes. But they actually have, it's a little bigger range than I might have anticipated there. These sorts of measures, I think, are more related to introducing a fish and then having it settle into some stable behavior. But again, looking at these varying aspects, I guess similar to the fish on the jig, you get these fairly large spreads until it settles into a mode around -50 for that fish. And there've been a lot of measures on tilt angle. This would be sonifying the fish from dorsally, but then looking at different tilt angles. And I think this work was done also on pollock, and was with some paired underwater video looking at fish around the edges of schools, and just trying to look at what their mean orientation was. For this work, what John Horn found was that the pollock actually, when they schooled, they didn't orient at 90 degrees to the surface. They had a center orientation about 10 degrees tail down, which he brought into some of his calculations and work.
Which fish were those?
Those were walleye pollock. This is marine stuff again. Again, same sort of thing. Other work we're looking at how krill, euphausids would orient, and in that case, really had almost a kind of 45-degree angle of incidence. And again, a lot of this was trying to track through from looking at what their backscattering properties of their oil-filled sacs, or I guess in the case of a fish, the swimbladder were, and then trying to look at what would be anticipated as that reflecting surface, and getting a better understanding of what the target strength meant relative to the animal. And things like zooplankton, of course, and to some extent you can get long, slow diel-vertical migrations that could change their aspect in the acoustic beam, depending on when the measurements were made. So here we're kind of back, maybe cutting to the chase, or to the end of all what we've kind of labored through here. But so first off, just a summary of the factors that can influence fish target strength. Fish orientation, we know that, we've seen that. Morphology, again, in a lot of the equations we're using, if we're mapping back to something like loves, it was across a number of species, fits reasonably well for fish of kind of a fusiform morphology, but again, it certainly has an effect. Presence, absence of a swimbladder, pretty obviously that's our 90% of our backscattering surface. So fish without or with reduced swimbladders would be expected to return lower target strengths for a given length. There is an effect to depth. We'll kind of rank these in a slide coming up, and due to pressure changes as the fish are, again, they're going to adjust their gas in their bladder to be neutrally buoyant, but that volume of gas is under a larger pressure at depth. We know kind of this one, but the variability in the amplitude of the signal, which again, target strength comes from that. It's corrected for where the fish is in the beam by the split beam systems, but if we've got other scatters, could be, fish in, it could be biological scatters, fish in zooplankton layers, or noise from non-reverberant, like a generator that's getting amplified, that can contribute to that amplitude, or it can be either additive or destructive, kind of depending how the wavelengths line up. So that'll increase your target strength variability. That's kind of that second piece. And then acoustic system effects, really calibration. Do we really know the efficiency of the acoustic system? Beam compensation would be that, what we call the beam pattern factor, correcting for those losses due to the beam directivity, for those echoes being off the axis. And maybe in the next little talk, when we go through some of the HTI software setup, we can talk about some settings we might be able to use in there to reduce the amount of beam compensation, or just include echoes that have less of it. Again, we can do it in a correct manner. We can characterize what those losses should be out to the beam edge, but you do have larger influence of any background noise levels on echoes near the edge of the beam. And sampling frequency, there are some smaller but measurable effects of frequency, and frequency is one of your acoustic system frequency is one of the inputs into loves, but you'll get different contributions of reflections from the fish at different frequencies, going from the lower ones that are used in fisheries acoustics to the higher. As far as the relative influence of the factors we've looked at, kind of mapping them all out, well, fish length was the largest influence on target strength, so that's a good thing. That's kind of what we're trying to tease out of this mess. And fish orientation being the next. From some of the earlier plots we saw, it's least variable if we're sampling them dorsally or ventrally. We sometimes can't do that. We need to capture fish close to the surface, and in those cases we set a threshold low enough to we have an idea of what those losses can be from head on to side aspect, and we want to, if we can, sample at a low enough threshold to capture our smallest fish of interest, but we really lose a lot of our resolution at side aspects as far as mapping it back to length. Depth being the third, and that's not something we typically are looking at or bringing into our target strength to length equations. It's a smaller driver, but it's there, and then acoustic frequency being the...
So the depth, so the sounder corrects for the effects of depth on the returning echo. You're just talking about the effects of depth on the size of the swim bladder, and therefore the...
Right. Now, I guess it could have an effect on your counts if you were, typically it's nice if you can collect to a minimum fish detection recording or threshold, maybe about 6 decibels below your smallest fish of interest, and I think you'd but there are some diminishing effects of, you'd expect a reduced target strength relative to the length to some extent for fish that are deeper in the water column.
Because we did look with that lake trout data, didn't see an effect, but I guess maybe that's more of a deal with marine systems where you've got
hundreds of meters.
It may be the domain. Yeah, you're definitely working down to depths of even up to 400 or 500 meters on some of those. But yeah, and it's a hard one. It really depends on your fish. You might expect some reduced target strength from a lake trout at depth relative to one shallower, but I think based on at least the relationships I've looked at, it wouldn't be, you might be looking at a decibel or something along that range over depths down to 100, 150 feet. Yeah, that'd be interesting to look at, because that would be, well, in general, that's what you found, where your fish were larger than your target strength would predict. Your fish were physically larger than your target strength would predict from loves.
Right, but that was basically with fish and sort of the common depth strata, but what we looked at was lake trout, so target strength, but we only looked at lake trout. Okay, yeah, so we looked at lake trout between 470 and 560 millimeters, so
okay.
Really narrow band, and they ranged from 10 to 30 meters in depth, and there's absolutely no relationship.
Nothing that you're showing or seeing there. Okay.
It's only down to 30 meters.
It may not be significant as far as the number of atmospheres.
That's 3 atmospheres, roughly.
Yep.
So, should you think that have an effect? But your picture was 10 atmospheres?
That one was 10.
Yeah, it was 10.
Yeah.
But there's got to be some kind of effect on it, because when we catch a netted lake trout from 175 feet on Bear Lake,
right,
and we bring it to the surface, that air bladder is huge,
Sure.
and it's hard to get that fish to go. So we have the lake trout descenders that are made by several different places, but they used them for rockfish originally on
Right.
the west, along the coast of California. And so we hook it in the jaw, and we have, I don't know, probably 30 to 40 feet of rope, and we hook it through the jaw and then grab the lake trout by the tail and then just let it send it down.
Right.
And you can watch it on your depth finder, and you sit there and jerk, and then that fish, you know, you send it down to that depth to decompress that swim bladder, and all we need is 1 atmosphere, so that's why we're sending it down there, and it makes a difference, because when you let it go, you can watch that fish literally swim away, where on the surface it's laying there going.
Right,
Yeah,
right,
so
no.
that's precisely because at depth he's adding more air in there to account for the pressure,
Right.
the shrinkage that would otherwise happen.
Right.
So,
But that's under greater pressure.
You're saying it's under greater pressure, and it's that greater pressure that's supposed to give you a different target strength. But it
doesn't show on there.
No, in the one graphic from, I think it was Blackster or whatever, I mean, he did show, I mean, again, just visually, but you could see, you know, from a cross-sectional standpoint on that fish, and it could have some influence too on the, you know, the actual shape of the swim, I mean, the, you know, the sort of shape of this, whether it's kind of a,
Right. Because it's compressing from all sides.
from all sides, right,
Pressure
you know, it's not
right.
necessarily a cylindrical body.
Right.
So you're saying it would just be a decibel difference?
Well, that was based on some plots I'd kind of just thumb in front of me type of thing. I didn't, at least over the domain of depths that we typically work at in freshwater, and then just looking at some of the marine work, which may not have been on the same species.
So I don't know if you'd be able to pick up a decibel difference. You know,
There's so much variability around it, so yeah, it may be so. So anyway, a lot of these we've touched on, but you know, sort of optimizing fish length estimates based on target strength. Well, we've already talked about that and looked at, you know, backscatter at different aspects on the fish. Dorsal and ventral are the least variable. If we're, you know, if we've got access to that data, that's definitely what we want to use in our target strength to length comparisons. You know, maximizing the number of echo returns will typically smooth towards some best center, mean estimate of target strength. Sometimes we'll do some work where we'll, you know, moor the boat or drift over some aggregations and try to get some extended series on the fish of interest, and then, you know, compare those means to what we're obtaining from our routine mobile surveys, and just see if we can get any additional resolution out of that. We can look at this when we do a quick walkthrough on just setting up the HTI echo sounders through the DEP sounder program, but and we talked about this, I think, in the last workshop, Kevin, that in some of the, if you're doing some controlled experiments, you can limit in the data record or even in your post processing, and just include echoes closer to the acoustic axis, maybe for a 15-degree transducer within 3 or 4 degrees of the acoustic axis, and look at the target strength means and variabilities around that set of data, and then compare it to your full set of echoes, and that'll typically, you know, reduce the variability in the mean target strength estimate. You know, even though those off-axis near the edge of the beam echoes are compensated, you know, the losses in the voltage due to them being on the edge of the axis is, you know, corrected in that target strength estimate. There's always some degree of background noise that'll have some contributions to those echoes near the edge. In the systems, there's also the ability to filter your fish target strength echoes to improve the what we call the single echo detections. And again, if you've got other fish or other targets in close proximity, you may get some energy that's contributing to your echoes from your fish of interest. And we expect, most of us are broadcasting, sampling at about a 0.2 millisecond pulse width, fairly narrow pulse width, just to get our best range resolution between fish and the bottom. And we'd expect that echoes coming back from a single target fish would be very close to that pulse width. And I think in most people's sampling setups, where you can also sample and select those echoes at 3 different power points or locations along that echo envelope, and can get more stringent on that to just to make sure you're not including contributions from other adjacent fish and targets. We usually don't want to get really stringent on those during data collection, because you can get some situations there where it'll drop echoes in valid fish, and we want to make sure we're tracking completely for counting purposes. But for target strength estimation, we can get a little more stringent. And again, as Kevin did and presented a really nice piece on, and again, this is, for a lot of us who are doing quick, we need to get a number and move on. We don't have the luxury of doing a lot of controlled target strength measurements, but there's definitely utility in it, and there's nothing, well, we'll get onto that about loves, but stepping outside of loves, I guess. And then, as I mentioned earlier, can reduce target strength variability by going down in acoustic frequency. But of course, most of the freshwater systems you'll see, it'll either be 120 kilohertz, 200 kilohertz, or occasionally 420 kilohertz. You'll definitely see higher target strength variability at 420 than 200. Some reduction going down to 120. The transducers are slightly more expensive. Going lower in frequency than that is usually just prohibitive for most freshwater users. You don't need the increased range depth penetration that you'll get, and they're just a whole lot more expensive. But so now moving on to loves, and Kevin did a good job of presenting really what that was kind of based on, and all the loves and a number of other relationships follow that 20 log length plus some constant that may include frequency and a couple of other parameters type form. And the assumption is that for an individual fish, the target strength, or the backscattering cross section of the fish, is proportional to the square of the fish length, meaning that as the fish gets longer, then that swim bladder increases proportionally to the square of the length. And loves, again, it's kind of amazing it's persisted that long. I actually met Richard Love way back when at some conference. He was kind of a funny guy. He was like, I think he was locked out of his hotel room running around with a towel around him. But
is he still alive?
I don't know if he still is. He was like 15 years ago, and and he was an engineer. He was an acoustics engineer. He wasn't necessarily a fisheries guy. And of course, the data at the time was done on tethered fish with a single beam system, and then really got a lot more utility. I don't think he ever expected it to really kind of take off like it did, but it gave that hinging, and then another decade from there, people could start to get in situ target strengths on fish. Really, the initial purpose of this was for people doing these marine echo integration studies. They'd do paired trawling. They'd capture some fish. They'd need to scale their integration data. They'd look at the lengths, estimate a target strength, and then that would go into the scaling for your numbers, which I guess I cover basically at the bottom here. And I'll show in a minute some other target strength relationships that some other folks have developed on the Great Lakes and elsewhere that kind of vary around what Love's put forward here, but so
now this equation that's applied in your HTI. What is it? I guess it's applied in the Excel spreadsheets when we.
it's more post hoc. I don't think we have it embedded in anything as
it would be in the Excel spreadsheets that we got I'm using as templates that we got.
I may have given you one. I've certainly done this in other equations in Excel.
We pull down the little menu. It says fish count after we paste in our file that we sorted and
right, to map
stuff,
it.
And we stick it in there and we hit fish count. That's where the Love's is applied.
I need to look at that again. You know,
I've got
a lot of that stuff. I know. I think I worked that up when I was working with you guys in like '95 or something, and kind of said, "Well, this will hold you till you figure out what you want to do."
Well, it's holding us.
And it's like it's become some sort of gossip. It's sort of like your stuff, I think.
It's like Love's equation, Pat.
Yeah, it is. You know, that's the risk.
Actually, Nielsen equation.
We don't have to want to change it.
Yeah.
No.
I don't, but I've also come to the conclusion I'd like to learn a little bit, whether today or this afternoon, of not necessarily using Kevin's thing since he's got it so tight for his Colorado reservoirs, but giving me the Rocky equation, but giving me I guess an alternative for processing my data, because
if it doesn't say what you want,
no,
yeah.
Dialogue.
You want to be a biostitute?
No.
Hey, Pat,
No.
Yeah.
go back.
I sure can.
I just I realize that some of the stuff we're using, for example, that fish proc program that we're using to sort, and we could do that some other way, but it's been tidy, but I want to, after that's sorted out, I want to look at that, because the fish count thing that Pat put together, and we're using them as templates to get our estimates, is that going to be compatible with, Excel 2015? Who knows if it will be.
Right.
And if it isn't, what, is there going to be a
Right.
alternative?
We got to bank you up for what, 7-8 years here?
Right.
Okay.
That's it.
That's it.
Well, you'll be done then anyway. Right?
Yeah. I hope so, but I don't know if the money thing's there.
We're all gonna retire.
Yeah. But no, we will look at that, and actually that's something we can kind of maybe talk through a bit on, just on kind of mapping what you've been
Afterwards, I'll
doing.
have my computer and- or
Yeah,
whenever
let's spend
it's
some time on
convenient
that.
to sit down and show you exactly.
Yeah,
what I'm doing.
because
I wish I would've brought my
definitely, one of the take homes from this is
analysis.
some action items, I think, just to work on and bring together before the next one. Did you get what you needed from that, Kevin? You're looking at just the form of the equations, and I'll show some examples of what other people have done, and certainly, like on Lake Billy Chinook, I know Steve Teesfeld had done a lot of work on kokanee, and he developed kind of his own derivation that.
What's his name?
Steve Teesfeld, Thiesfeld. He's still around. I think he's bounced from.
Is that one of the published ones, or? I guess I need to go back and look at which ones I've got.
I'll look and see. I can actually give you that relationship he was using in an Excel sheet.
Okay.
I don't know if it would be published in some ODF and W reports, whether it's in peer-reviewed literature or not. But that was a fit towards kokanee that I think might fit in with kind of what you found, because he was using, I think, 24.9 as his M constant, and it would have driven I think your equivalent target strength lengths to a longer length estimate. I'll show some of those in a minute. So again, just kind of circling back there, so that whole sort of centering somewhere around that 20 log length being an approximation for relating length target strength. And McLennan and Simmons, the Fisheries Acoustics book, I was kind of waving around. They waffle a bit here, They weren't coming in hard behind it, but they really came back to, well, it seemed a fair assumption that target strength being proportional to the backscatter and cross section of the swim bladder, and that swim bladder being roughly 90% of the fish body structure that's contributing to that backscatter. That it seemed a fair assumption. Being English, I guess that means they weren't saying yes or no. And then, like we've seen here, well, not so much maybe just that, we've seen here that sort of loves, which is very close to a 20 log. I think it's a 19.1 constant with an intercept, was imperfect. There's been folks who have been looking at other target strength length fits that don't follow a log form as well, a little more on the fringes and specific to their application, but they're definitely out there. This reference at the bottom here, Sam McClatchy and George Macaulay and so on, again, and these folks they're New Zealand, Australian researchers working more with deep sea fishes, but they published a paper, a requiem. You could have used requiem in your talk, yeah. Or eulogy or something. I guess we'll give that a year, then we'll give it the eulogy. So there are certainly people looking at fits outside of that.
Do you have a copy of that ICs?
I can get it. I don't know if I have that one electronically, and I was looking for the Aglin paper. I know I promised that to you. I'll give you a copy of. It's actually the book that's in the back, which is the Great Lakes Acoustic Standard Operating Procedure. I've got that as a PDF, and it's got a pretty literal translation of Aglin with examples in it.
Okay.
And then I'll follow up with the paper. I thought I had it locally. And this is a little bit of an aside, but some other research, again, kind of back to the sorts of things my major professor John Horn was doing. This was for tuna, but they were looking at swim bladder volume relative to length, and as you can see here, that's not following that's really following more of a power function than a linear log function. I guess the aside to that, because that hasn't really been brought home. I mean, they did this more as an exercise in anatomy where they were catching a whole length range of fish and then doing surgeries on them and measuring swim bladder volumes and so on. Again, for tuna, doesn't necessarily mean, because we got to look at swim bladder shape and so on, that the acoustic cross section doesn't have a generally 20 log length approximation. And looking back, again, we've looked at data from Kevin, and you can certainly find it from others where you'll see even bigger scatter and some anomalies in your paired catches. This actually was Kokanee. Was it Kokanee? It's up on Lake Osoyoos. I think it was Kokanee in BC, where they had paired trawl and acoustic system, and again goes back a few years to sort of the mid 80s. But they Tracy Stagg, who's at HTI, and Bill Karp, who I used to work with, and he's at NOAA now. But again, you see here the means line reasonably well for this set of data, but we see a lot more. Well, we see more spread in the acoustic estimates of target strength due to that variability. So you can certainly find examples where you'll get what you'll feel are reasonable fits with loves, but it's not universal from what we've seen. So just sort of my summary, and I can backpedal on a couple of these based on what Kevin said. But, you know, we certainly recognize, and, you know, we kind of came into this one looking at all the reasons it could be different. You know, being good scientists, we find somebody puts forward a simple answer, and then we can just cut it down. But we, you know, it is an imperfect estimator of absolute fish length. And, you know, is influenced by a number of factors. Fish length is the biggest driver on mean fish target strength, but certainly aspect would be the a big influence, and then you know, followed by some other factors. Depth has an influence, much lesser, but. Again, a lot of just this work, like what Kevin showed, just kind of understanding the backscattering properties of our fish of interest, and then there are some things we can do acoustically to minimize the impact of noise and some of the other potentially things that can skew our results. This kind of comes back to, again, what Kevin was talking about in survey design. You know, we know these relationships are flawed. They're in the literature. They're widely distributed. You know, so we tend to keep using them. But there's a lot of researchers out there that have presented refined target strength length relationships, and then, you know, use them for their data going forward. And it's certainly defensible. You know, loves, you know, and I continue to use it as a you know, generalization for my work, but it's not like a religious piece or anything quite like that. So maybe where I'll go from
That slide that Kevin showed of the fishes that were used to determine or make Love's equation, I didn't know what half of those fishes even looked like.
yeah, and this is all over in the
I had to
UK.
look up those fishes to see what body shape they were, because I wanted to find out if are those, you know, we're using it for Cisco, and we're using it for kokanee, and we're using it for shad, and, you know, is it reasonable, you know, just based on the morphological characters, not knowing what the Swimbladder looks like, but kind of thinking that you have a long, skinny, fusiform fish.
Right.
The bladder's going to be fairly similar to the shape of the fish, you know, unless you have some really strange, you know, development in that fish. But most of those fish that they use, even though they were saltwater fish, they were remarkably similar in physical shape to Cisco.
Right.
And I talked to Dr. Lukey about that and said, you know, you use Loves. Do you believe that? Did you use it because that's the only thing out there, or did you use it because it really did, you know, come close to the, you know, did it come close to looking like what we would expect Cisco to look like and stuff? And they tried to tether Cisco and stuff like that, and they didn't have any luck with that. And,
See, I think that's the bigger deal. Is not so much the fish they use, but the fact the fish they use were either dead or anesthetized and tethered.
Right.
And that's the one thing you see from when you hook these things.
Right.
I mean, it's totally different.
Right.
You know, so I think that's the bigger deal, and that's why I think the ice fishing is compelling, because that's the fish on his own coming into the beam before anything happens.
Right. Right. No, and that was good. That was really that was intriguing data, and it's.
But I think
Have you tried to do a fit? Have you tweaked a fit to that? What you would find as a best fit?
Yeah, and so I guess I'm curious. You were saying in your last step, you said that it'd be defensible to explore variations.
And here's a few that are actually in that Great Lakes.
But those are still all the 20 log.
These are 20 log form, right? And you really weren't finding a linear fit on it. Is that what you're saying?
No, I'm just saying this is what I was exploring. But you said in your last one that it was dispensable to explore variations.
Well, they're out there.
This is the variation. I thought you meant explore a different form of,
it is.
You know, something like
Well,
a power function or something.
I would say that those are out there. They aren't shown here. I'll give you an electronic. They actually describe and discuss it fairly well in that Great Lakes Standard Operating Procedures
Okay.
manual. But there are folks that have done, sort of like a power function or something that would sort of hinge more on a swim bladder volume than a.
And I'm not
Than a
saying
surface
that
area.
would be the way to go. I was only exploring this form.
Right.
Because that's what others have done. And
I mean,
I'm
these
wondering-
are some that are out in the literature.
Which table is this from?
This
Actually,
this is that I'll give anyone who wants it. I can give it to them electronically. It's that book that's in the back, the Great Lakes Standard Operating
This one is from
Procedure.
Great Lakes Standard.
And so I just brought up. Rather, I didn't quite get this in a slide. I just brought up the PDF of the manual. But like here, Scott. I mean, there's one that's Lars Rudstam out of Cornell.
He has one for smell too. Yeah, there it is.
Has
the
been
2003 one, and that would probably be pretty close too.
And now you see that one's not. It's not. Well, it does. The intercept, I guess, would be about might make about a 4 or 5 dB difference. And the Cisco, it's walking a little bit the other side of.
Yeah, but like I said, that's Great Lakes Cisco, and so there's the smelt would be probably closer
close,
to
right.
Bonneville Cisco than the
Right.
actual Cisco listed there. But if you look at them though, like you said, it makes some difference, but not a lot. And since again, it was one of those things, do we want to go back and apply that equation to
No.
So how
20
do
years
you,
worth of
I mean,
data?
I guess I would look at your, if you're gill netting these things, just do that. If you're good at gill netting, just set the gill net, run the deucer around it, and then see if you see, if like that graph Pat just showed where your sonar data really does line up well with your netting data, then you're probably fine. But
Right.
If like the Williamsport situation, you've got, your mean spawner size is 35 centimeters by love, and yet when you measure them a month later, they're all 50 centimeters.
Right. And of course, for your work, Scott, I mean,
We're talking a narrow range of size.
you're talking a narrow range of size. You're really looking more at a population estimate
Right.
than really trying to break it
And
down
at
into
smaller
a.
sizes, there's less difference in
Right,
in
and
love, so.
the other thing is treating it, what Kevin had mentioned also, is we're calling it a population estimate when it's really an index number to go by,
Right.
and that's what we care about. Is the population going up or down,
Yeah.
or is it stable?
Right. And index work
we
is.
have a rough number there, and we do put our little error bars around it, and like I said, I'm happy with plus or minus 40% of that mean.
Sure.
But what I'm more concerned about is that trend going down over a 10-year
Right.
period? Is it going up or is it horizontal? And to me, that's more important than anything.
Yeah,
And
because
so-
we're dealing with it from a management standpoint,
Right.
not a research standpoint.
Yes, yes.
So
And
you don't need a
no.
real great number, you just need to say how.
Where we needed the great number was when we're in Granby trying to predict
Right.
the following
Right,
year's
that-
intake.
Right.
That is
yeah.
extremely
Yeah.
important.
Yeah.
Right,
Right.
absolutely.
Right.
Yeah, I'm just saying,
Yeah.
in
Right.
our situation here, we don't always need it.
Yep, when you're dealing with, short-lived fish, 4 years old, they're out of the system. And so
Right.
you can make that call, they're not to spend 2 weeks setting up a trap or
And
not.
they're fast growing fish, so
Yeah,
you actually
right,
can see
right,
bumps
see 'em,
in the length
yeah.
frequency.
That is, so yeah. Yep.
Right.
See the utility of doing it both ways. But this rud stand, that's the one I was talking to Lukey about. I said, hey, they developed this for smelt and Cisco and even alewife. I mean, Cisco is probably between a smelt body and an alewife body. Smelt are more even fusiform, I think, than Cisco. And Cisco are in the summertime. They're,
Right.
fatter,
Or
taller.
hell, an even easier thing would be just to go ahead and generate a plot, take 100 fish lengths that you've got.
Yep.
And back out what it'd be with loves versus
Yep.
this one, and just see if there's enough of a
Yeah.
difference in a 10-centimeter fish
Yep.
to even
Right,
worry
right.
about.
Yep.
And see,
Right.
you're lucky because you know that out in the pelagic in that depth strata, all you've got is
Cisco,
Right.
right? Because we're not partitioning by species.
Right.
'Cause- and like I said, I've got it easy compared to you, where you're looking at multiple species. Ryan's got it easy because he knows the majority of those fish out there in the upper,
Right.
column are kokanee, and
Right.
so
But yeah, once we started applying Love's equation to our target strengths, we saw the same thing you did. It was drastically underestimating what we knew was out there. So any chance of splitting out species based on depth and size wasn't really going to work for us. And so I just stopped doing anything trying to correlate target strength with total length or any length measure until we can get some better data.
Right, right. And this is just a graphic that shows the Guy Fleischer, who had done some other work on the Great Lakes. He was the one who really stepped maybe furthest away from but all those other sort of refinements that we saw there with the with that 20 log length form. I mean, there are certainly differences, but you can kind of see that they're.
And this is in the same manual?
Yeah. Great Lakes SOP.pdf.
And see, it's figures like this that trouble me. Obviously we all have issues with the tethered fish. They were anesthetized or dead, but I can't remember if it was 19 centimeters or 23 centimeters. Those numbers stick in my head. Was the maximum length of any fish that was used in
Right.
Love's equation.
Right.
And then everyone's extrapolating it out.
No,
to
you're right.
12 meters.
You're right. And I mean, I've done work in Alaska with salmon where it definitely was falling apart for big fish.
The figure you shot obviously was based on volume, but for tuna, if you look down at the bottom there, it fits pretty linearly. But once you get out to those larger fish sizes,
Right.
then we've got that power function, and maybe that's why when we're looking at
Right.
20, 30, 50 centimeter long fish, Love's isn't fitting nearly
Right.
as well as what it may have if it was based on.
Right. I would agree with that. I mean, just based on some things I've observed. So anyway, well, I guess we won't wrestle target strength and length to the ground on this one, but we talked in our last workshop about some controlled experiments, and again, most folks here, other than Travis in his spare time, are doing pure research, right? But it is worthwhile. I mean, as I've had opportunity, we were doing some work down in Puerto Rico and just had some dead days, and they had a big fish cage and went through and just measured time series on some different species down there, and you do get a lot of different kind of morphology on a lot of those fishes, but in general, Love's wasn't way off, and it's kind of interesting. It was just data I threw in as an aside to a report, and it turns out it's like the only work that's ever been done down there, so I still keep getting calls on it. It's like, I don't know, we just had an extra day and threw some in a cage, but it's. And it is, I mean, it does. Kokanee, I think, is the one that just keeps coming up and up, again and again, because people are, do have that need and desire to really look at the age classes walking through, and up in, I know on Lake Koocanusa or Wallowa in Oregon, or, that's basically what they're doing, and in fact, I was just talking to some. Who was it? Oh, what was his name? He took over for some of the work on Lake Wallowa, and he was doing really hard apportionments down to like the 10th of a centimeter, translated from Love's, and I'm like, well, it's okay if you're sort of just looking at it as a trending, but I mean, your fish of interest are clearly on either side of the boundary. If you assume, it really depends what the distribution looks like, right? Whether.
Well, and I should have thrown this figure out that I tossed, the one that looks at lake trout by depth. I mean, we're looking at a range of, what did I say it was, like 10 centimeters or 20 centimeters on these fish?
Right.
The range of decibels that show up.
Yeah, you're just basically, any sort of like a depth effect would just be totally masked in the variability you're seeing from.
Yeah, it was, so going from 47 to 56 centimeters, so 10 centimeter range, and our decibels, our mean target strengths range from minus 44 to minus 35.
Yeah, so you've got a 9 dB swing there.
Swing, and fish that are only 10 centimeters different in length.
Right, and then what Love's would predict, or what you'd based on that would be 6 dB is a doubling in length.
Right.
or a halving in length,
So
depending.
6 dB is doubling length.
Right, because it's, in just the decibel scale, as Andrew mentioned the other day, it's, a 6 dB is a factor of 2 in voltage, and then, really we're just mapping that back to length. So, based on loves or those forms, they're just assuming then that the backscattering properties of a fish twice the length of another fish are 6 dB greater. So
I'm just figuring out mine. I was just wanted to make sure after all these years. I know I did this before. I just don't remember it. But
right,
yeah, we have a 12 decibel window that we're looking at Cisco, and so we start at 2 and go up to 8 inches, and so that's good. So 2 and double that is 4 and double that is 8.
Yep.
So that's exactly
Yep.
perfect.
You got it. You got it.
And so, anyways, so that's because we're going 2 to 8 inches, and 2 to 8.5, but we're also 12.4.
Right. So, okay.